Welcome everyone, I am Ujjwal Pal. Today we will solve a LeetCode problem step by step. The problem number is 2458, which is height of binary tree after subtree removal queries. Let's see the problem statement. You are given the root of a binary tree with n nodes. Each node is assigned a unique value from 1 to n. You are also given an array queries of size m. You have to perform m independent queries on the tree where in the ith query you do the following. Remove the subtree rooted at the node with the value queries I from the tree. It is guaranteed that queries I will not be equal to the value of the root, which means the query I value will not be 1. Okay. Return an array answer of size m where answer I is the height of the tree after performing the ith query. Note that the queries are independent, so the tree returns to its initial state after each query, which means we do not have to delete the subtree like permanently. We will do that virtually, and we have to make the tree again in the initial state. Okay. Next, the height of a tree is the number of edges in the longest simple path from the root node to some node in the tree, which means there is it is the height of the tree is not the count of the nodes in the longest path. It is the count of edges. Like in this example 1 4 5 7, it is the longest path, so the answer will be 3, not 4. Okay, the height. And let's see the constraints. The n will be up to 10 to the power 5. Each of the value will be 1 to n. All the values are unique, and length of the queries will be m, which is minimum of n and 10 to the power 4, and queries I will be 1 to n. Queries I will not be less equal to 1, like the answer says that it is guaranteed that the like it is guaranteed that the queries I will not be the root value, so root value is always 1. So you can assume that this is not less equal to 1, it will be greater than 1, and that's it. So what we need to do? First, what it says, we have to perform the queries I, and after performing the queries I, we have to return the max height of the tree. So to do that, first we need to have some data. Which data? For each of the value, we have to calculate the height from that node to the bottommost element. So we will calculate height for each of the node from that node to the max height we will calculate, and also we need to calculate the level also, like for which level we are calculating that, and for each level we will create a priority queue, or you can do whatever else, but I will use here a priority queue to store the max heights. Like we will use priority queue to store the heights of each level. Like we will create another a another map, and in the map the key will be the level value, and the value will be a priority queue which stores the all the height along with the values also. Okay, this is we need to do. And another thing, to get the the level of the any node, we also create another map which will store only two things. Key will be the value, node value, and the value of the another map will be the level. So, and we will do that by recursion. So let's start. First, we need unordered map in comma one priority queue, because here this int will store the level and the priority queue will store all the nodes along with their heights, and we will keep the first element of the priority queue as the height, so that our priority queue stores the priority wise the height. We need the height, max height each time. So we will keep the height as the first element, and the second element will be the root value. Okay. So priority queue. priority queue. First one will be int, which stores the height. Second int will be the value. That's it. Let's say it is pq, and one unordered map to store the first int is the node value, and second int is the level. Okay, let's say empty. First, let's calculate the data first. So to do that, let's create a function helper, and it will take the initial root value, current level which is 0, and also it will take the priority queue and the map. That's it. And as we will create that, we need to check the height. To calculate the height, we will also take help of the helper function also, so so that it will return the height of the childs. So as we do not need the height of the root element, so we will just add underscore here. Let's create the function first. Helper, first one is the root node, which is root. Second one is the level. Third one is the priority queue. Let's copy paste, and we will take the reference of that variable. Do not take the actual variable, take the reference variable, because we need to reflect the changes to all the call stacks. Also, reference of this map. Now we need to write the function. So first we need to check if root is not present, then just return 0. Because if the root is not present, then the height will be 0, because this helper function will always return the height from the current node to the like bottommost element of this subtree, which is starting from that current node. Okay, so if the root is not present, return the height as 0. Now to get the height of the current element, first we need to calculate the left and right. For left and right, we will call the helper function. It will give the height of left and right. Then we can calculate the height of the current node. So left is equal to helper root left, level will be level plus 1. Then also we need the priority queue and map. That's it. And same as for right. And after getting left and right value, we need the max height. So in, let's say, height h equal to max of left comma right. That's it. Now we got the height, and we also have the level of the current line. Now let's store it in our queue and map. So map of root value, we need a map of root value as the height, like level of the current level. So level is that, and in priority queue, the queue of the current level, because the priority queue is the first one. This are not aware, like it is the level. We will create the priority queue as a level wise. So pq of level will be, not will be, it will, we will in priority queue we will push two things. First one will be the height, second one will be the root value. We need the root value in priority queue because each time when we are deleting one element from this, because we need in query we will have the value of any random node. So whenever we are deleting one node, we need to check the like most height, like the in that level, which is the maximum height, that is one level got. And we need the value because to check if the maximum height is the current node which we are deleting, then we need to consider the second height. So that's why we need the value also to check that. And after storing the priority queue, that's it. This function is done. Now we need to create answer vector, vector int answer, and for each of the queries, we need to calculate the height after deleting this subtree which is starting from this IT. So answer dot push back. We will calculate we will create another function to do that solve, which will take the value from which with the subtree starting the level of that node. So to get the level, we will get it from map of IT, and we also need the priority queue to check the height of the like sibling elements. So after that, we will return answer. That's it. Now we need to create the solve function. It will return integer solve, and it will take first one is the value, second one is the level of that value node, and third one is the priority queue. And this priority queue will also take the reference. Now we need to check if there is any sibling or not, because as we are deleting the node of the current level, so we need to check if the pq of level dot size. Pq of level gives the priority queue of the current level. We will check if the size is equal to 1. If the size is 1, which means the only one element present in the current level, which is the value, because we are deleting that. So if it is the current level is contains only one node, that means the maximum height of the whole tree will be the level minus 1. Why? Because if the current level contains only one element, that means there is no other sibling of the current level. And if there is no other sibling, that means like a tree will not have any element after the current level besides the current value which we are deleting. So then the maximum height will be level minus 1, because the parent of this current value will be the last element of that whole tree. Okay, so level minus 1 will be the max height. Else, if there is sibling, we need to give the height of that calculate the height of the sibling. So first we need to check, let's say sibling is s1. S1 is pq of that level dot top. If we need to check if the sibling, like the height of the maximum sibling is same as the current node or not, because the current node is also present in the same level. We need to check that if s1 dot second is equal to value or not. If it is value, then we need to consider the second sibling, second highest. Okay, and else we need to consider the second element will be, first we need to pop it out, pq dot pop the first highest we pop. Now auto it, not it, auto s2 is the second highest, pq of lv dot top, this is the second hash, and we need to return the tree in initial state. To do that, we will again push pq dot push the element which we have popped. So the element is s1. Now we in s2 we have the second hash. So the second hash we need to return the whole height. Second hash in priority queue we are considering the height from that level to the bottommost element of that subtree. So return the height. So s2 dot first, it will give the height from that level or that element to the bottommost, and we need to add the level, because we need the ultimate height of the whole tree, and the whole tree's height will be from root to current level, which is lv, and the height from that level to the bottommost element, which is s2 dot first. That's it. And else, if the second s1 dot second, which means the highest element, like the element which contains the highest height, it is not same as the node which we are deleting. That means we need to return that level, which is s1 dot first, it will give the height from that level to bottommost, and plus LV to get the height from root to that level. That's it. Now let's see will it work or not. Okay, there is an error, which is because we are declaring the priority queue in a wrong way. It is not only incomment, it is pair of incomment, pair of incomment. Please correct that. It is pair of incomment, and the data type will be updated in all place. So update here and also update here. And I am seeing there is another problem, which is this is int. We are not returning anything. So with the return will be return height plus 1, because this height is the max height of child. So height plus 1, it will be returned. And another thing is this is not pq.pop, this is pq of lv.pop. Okay, this will be pq of lv.pop. That's it. Now let's see will it work or not. It is accepted. Let's submit it. So it is accepted. Let me discuss the time and space complexities of this algorithm. So the space complexity of this priority queue is big of n in most case, because we have to store the element along with the height. So for all the elements or all the nodes present in the tree, so it is in most case there will be not most case, there will be a number of values, and where n is the number of nodes. And in map we are also storing the like each node along with the level of its level. So it is also taking big of n time, big of n space complexity, and this answer is taking big of m space complexity, where m is the length of queries. This will, so overall space complexity will be big of max of big of n comma m. And the time complexity, this for loop is running m times, and for each of the time it is calculating the solve function, and this solve function in host case it will take like in host case it is popping from the priority queue and also pushing in the priority queue. So this pop and push function is taking big of log n time, where n is the length of priority queue, and it will take log n time. And so overall time complexity for this for loop will be big of m log n. Okay, where m is the length of queries and n is the length of priority queue. And this helper function, it is taking calculating the height and pushing it to the priority queue. So for each of the element it is pushing it, this pushing function to priority queue, it is taking log n time, and adding the level in the map, it will take constant time. And we are doing it for all the nodes present in the tree. So overall time complexity of this recursion function, it will take big of n log n time, where n is the length of, or not length, where n is the number of nodes present in our tree. So overall time complexity of this overall algorithm will be n m log n. So thanks for watching. If you want to check out the code, you will find it in the description box below. So that's it for today. See you in the next video.